Hello students, in our previous lecture, the whole session of the last 6 lecture was on the slope deflection method. In that case, we have studied number of types beam, 2 span continuous beam, 3 span continuous beam with different loads, with different end conditions. They are solved by slope deflection method. In that case, what we are going to do, first we have to find out fixed end moments. After that, we are putting the equation of slope deflection for each individual span. After that, we were put the conditions of equilibrium. From that condition, we will get the rotation of particular joint, that is called EI theta, which will help us out the finding out the support moment of each support. So for the finding out the bending moment and slope deflection, in slope deflection method we will use the different step. Now we are going to discuss on moment distribution method, which is also useful for the finding out the shear force and bending moment for the continuous beam. So dear students, slope deflection method and moment distribution method both are same for the finding out the slope deflection method for the continuous beam. The moment distribution method was studied about you in our previous subject SA1, but in that case you were studied about the only the introduction of moment distribution method. Now we will discuss the whole moment distribution method in deep. So from the name of this method, moment distribution method, in that case we can understand something from the name. There is some moment that we have to distribute in a proper manner on the support, that we had done in our previous method. In that method, we had understand that the each support getting the same moment by the balancing of that fixed end moment. So here also we are going to do the same procedure, but the little bit difference in calculation. So dear student, for the understanding of this moment distribution method, we have to follow some steps and the nominal criteria for the getting slope and deflection method. So in this lecture, we are going to understand about the introduction of moment distribution method, important terms which we are using for the MDM, sign convention, at which point we are going to take plus moment, minus moment. So all that sign convention is going to discussed in this lecture, fixed end moments, and after that examples, simply supported beam with and conditions are different, fixed support with sinking of support. This kind of examples we will discuss in these lectures. So first let's start with introduction. The moment distribution method was first introduced by Professor Heidi Cross of Illinois University in 1930. This method provides us a convenient means of analysis of statically indeterminate beam and the rigid frame. in this method we can solve the frame by the simplest way. It is used when a number of redundants are large and when other methods become very tedious. Suppose if we have to find out the 5 span continuous beam, then the slope deflection method is not reliable for this kind because the calculations are lengthy for that method. But in the moment distribution method we can find long span with number of support easily. So for this method we have to understand about the stiffness. What is the stiffness that we know, but in for this lecture we have to understand stiffness in the term of relative stiffness, the moment required to produce the unit rotation, that is slope, at the simply supported end of the member is called stiffness, and here we will use the sign of K for the stiffness. The stiffness when both ends are hinged, stiffness when both ends are fixed are the different for this moment distribution method. First, beam hinged at both ends. So whenever we will find out the moment as well as rotation, then what's going to done? Suppose the both ends are hinged, then moment is MAB upon theta AB is equal to 3 EI upon M. Means the moment required at A to induce the unit rotation, that is 3 EI upon L. When far end of B is free to rotate. Here the rotation at the point B is done because it is simple support. So from this 3 EI upon L we can get the moment. This moment required to induce the unit rotation is called stiffness, and it is denoted by the K that we discussed. Now beam hinged at the near end and fixed at the far end, like this. At a near end it is hinged, but at far end it is fixed. Then it will be changed, like MAB is equal to 2 EI upon L 2 theta A plus 0. That is MAB upon theta AB is equal to 4 EI upon L. For this situation we have to take this moment as 4 EI by L. That is the moment required at A to induce the unit rotation at A is the 4 EI by L for this kind of situation when the far end B is fixed against the rotation. So here the rotation is 0. At that time moment induced at this point is 4 EI upon L. Now from this moment we have to find out the carryover factor, because here we have to distribute the moments in some manner. So for that we have to carryover factor for the distribution of moment in the proper way. So a moment is applied at the near end induced at the fixed far end. A moment is equal to the half of magnitude in the same direction. So what here we are going to do, if our far end is fixed, then the distribution of moment in half means the half of applied moment at the near end is carried over the fixed far end, and carryover factor is 1/2. This is the most important thing for the finding out the carryover factor. Now after that we have to find out the distribution factor. What it means? From this distribution factor we can understand that at this point we have to distribute this much moment only. So the moment is calculated by us in the form of fixed end moment, and that moment is distributed by multiplying of this factor. The factor in which the applied moment is distributed, the member is known as the distribution factor. If far end pin means it is hinged, then distribution factor is 1. But if far end is fixed, then distribution factor is 0. These two things is most important for us. From that we can get the distribution factor at the ends. But here at the intermediate point, when at some joint there are two members are connected and suppose three members are connected, at that time this distribution factor must be changed. And how we can get this? Let's try to understand. Suppose some of the number of members are connected at a joint, then the far end of that joint is hinged, then the moment for that particular point is 3 upon L. Suppose we will take that member is number 1, then it is 3 I1 upon L1 into theta, that is called K1 into theta. Same for second member, the far end is fixed, then it is 4 I2 upon L2 theta is equal to K2 into theta. At 3, the moment at third beam for the 3 I3 upon L3, right? For the understanding of this, what we are going to do, we have to finding out the moment, that is 3 upon L or else 4 upon L. We have to summation of that moment. Suppose we want to find out the sum of that moment at a particular joint. So what we are going to do, we have to sum of that moment divided by the whole moment, so we can get the distribution factor. Now the most important thing, that is sign convention. How we can get this? Support moment, clockwise moment is positive and anti-clockwise moment is negative. If we are talking about the rotation, so suppose the rotation is clockwise, then it is positive and anti-clockwise moment is negative. Here we have also used the sinking of support, means sometimes due to the heavy force our support will be deflect in downward direction, that is called sinking of support for particular this term. Now sinking means it is the settlement. The settlement will be taken positive if it is rotated by the beam of a hole in the clockwise direction. But the settlement will be taken as negative if it is rotated by the beam as a whole in the anti-clockwise direction. We know about the clockwise and anti-clockwise, but whenever our settlement is somewhere and due to that our moment is generating anti-clockwise rotation, at that time it is negative, but the moment is induced positive, then it is clockwise rotation. Clear? Good. Now we know about the friction moment. In the last method we can understand about the fixed end moment. So you know about the friction moment, but here I have taken some simple example that repetitively used in our examples. So in that case, the friction moment for the various load cases is shown in the figure. First, for the centric loading, means the point load is acting at a center and the whole span length, that is L, and the centric load, that means it is acting L by 2 and L by 2. Due to this load, our moment is generating at the fixed end, that is PL upon 8, and it is also PL upon 8. But left side it is anti-clockwise, then it is minus. And here it is clockwise, then it is plus. So we have to take in consideration that the left side anti-clockwise and right side is clockwise. Now another case, for the eccentric loading, UDL, rotation, sinking of support, and UL. These all things are over here. And for that, first we have to take eccentric loading, means a load is acting on a beam having span L and it is fixed at the both end. At that time, eccentric loading is acting at A distance from left support and B distance from right support. In this case, the generating support moment is anticlockwise and clockwise. Anticlockwise moment is PAB square upon L square, and over the right hand side it is PA square B upon L square. This equation is frequently used by us in our previous lecture, in previous method. Now, if the UDL over there means a fixed beam having span L and the UDL is over the entire span, at that time the left side moment is anticlockwise and right side moment is clockwise. The left side moment is minus WL square upon 12, that we know. Here I have taken Q as a loading, means here it is QL square upon 12, and right hand side QL square upon 12, but it is plus. So these three condition is frequently used by us in our all the examples. Now, the fixed end moment for the sinking of support, it always taken as minus 6 EI upon L square. It is most important thing. Suppose here we are considering that sinking of support, but due to the rotation of member, if that is clockwise means it is positive and it is anti-clockwise, then it will be minus. So this is the most important thing. Now, how we can calculate these things? For that, I have taken some simple example for the understanding of this MDM that you had studied in SA1. So it is very much simple for you. Here I have taken the 3 span continuous beam which is having UDL on A to B and B to C, that is 20 kilonewton per meter, and the length of this span AB is 6 meter, B to C is 6 meter, and C to D also 6 meter, and another load acting on this span, that is 40 kilonewton at the center, means at the 3 meter from left support, the 60 kilonewton on BC span and the 80 kilonewton on CD span. So here it is a merging of these two loads, UDL as well as the point load at the center. So what we have to do? We have to first find out the fixed end moment, and we have the equation for fixed end moment for AB and BA, right? First we have talking about the AB. What we will get? If it is UDL, then WL square by 12, and if the point load, then PL upon 8. We have two summation of these two, but it is symmetrical loading, so left hand side minus 90 and right hand side plus 90 moment is there. It is called fixed end moment of A to B and B to A. Now for this span BC, fixed end moment is negative, for B to C and C to B it is positive, but so symmetrical loading is there, so we have to take directly equation WL square by 12 plus PL upon 8. So it is 60 plus 45, means it is 105 kilonewton into meter. And third one, it is a fixed end moment C to D and D to C, means PL upon 8, that we know. Left hand side it is anti-clockwise, means negative, and right hand side it is positive, and the value is, we will get 60 kilonewton into meter. So students, here our first step, that is finding out the fixed end moment, and it is repeated again in this method also. So the distribution, for this we have to finding out the distribution factor, and as we discussed, the distribution factor is most important thing for the distribution of moment which finding out by us as a fixed end moment. So here we have four joint A, B, C and D. For A, we can take directly distribution factor as 1 because it is a simple. Now B and C is the common joint. So at B it is BA and again it will be to C. Far end is simple, then it is 3 EI upon L as we discussed, and B to C is continuous. Continuous is taken as a fixed by us, so it is 4 EI upon L. We have all the values and we can get the stiffness. Now what we have to do? We have to summation of these two stiffness, it is 1.16 EI. Now for the distribution factor we have to take K upon sigma K that we discussed. So K upon sigma K, that is 0.43 and it is 0.57. So at B joint we will get the distribution factor. At C joint same, C2B and C2D. C2B is the continuous, means take here 4 EI upon L, and that is C2D is simply supported, means it is taken 3 EI upon L. Again summation of these two and we will get the distribution factor. At D point it is simple support, so we will get the 1 as a distribution factor. So this table is important for us. Now what we are going to do? We will take the distribution table for the understanding and how we will get this distribution. So our first joint is A, B and C and D. We will put over here and take one reference line from that. At A our distribution factor is 1. Here our distribution factor is again 1. But B to A, that is 0.43. Here I have taken the precision at third level. Here 571 point. At C, C to B is 0.571 and C to D, that is 0.429. So first we have to write down our distribution factor at each joint. Now we had find out the fixed end moment, that we have to return over here. For A to B it is 90, here plus 90, here minus 105, plus 105, minus 60, plus 60. This is our fixed end moment. And dear student, the most important thing that we have to remember over here, whenever our end supports are simple, then we have to take 0 moment over here. So how we can get 0? It is 90, then take plus 90, so it is 0. Here it is plus 60, then take minus 60, it is 0. But whenever we are going to do this moment, so we have to half of this moment is taken by us over here, and here also half of the moment taken at C. So now finally what we will get? We will get the initial moment for the distribution of the moment. So here it is 0, summation of these two is 135, this is minus 105, this is plus 05, this is 90 and this is 0. Now we have to take distribution, and how we will take this distribution? We have to multiply this support moment with the distribution factor. Here 0 is multiplied with 1 is over here, means it is 0. So at simple support all the moment must be 0, so we can take directly final moment as 0. But here we have to summation of these two and multiply by with this distribution factor, we will get the value minus 12.87. Again summation of these two and multiply with this, we will get the 17.13. Clear? Now at the C point, summation of these two and multiply with this, we will get this much value, and here again summation of these two and multiply with this 4 to 9, we will get the 6 point. Now carryover. We know about the carryover. Whenever the carryover is done, we have to take half of this over here and half of this over here. But here it is always 0. So here 0. But this half of this over here and half of this over here. Right? Now again distribution. Then the here is 0. So summation of these two and multiply with this, then we will get this much. Again this value and multiply with this, we will get the 2.445. Now here this much value 8.56, it is negative, and some here value is 0. Then summation of these two value and multiply with this 0.57 means we will get this one. And again this summation of these two and multiply with this value 0.429, we will get the this much. So the again carryover is done by us, because at what level we have to this process repetitively, whenever we will get the distribution of 0 point something and nearby the 0 point something, we will stop the distribution and carry over there. So again the carryover of these two, half of this over here and half of this over here. Now summation of these two and multiply with this, we will get this much. Again summation of these two value and multiply with this, we will get this much, right? Same procedure over here. So still we can continue with these two. Again we can do carryover and distribution, we will get the exactly value, but whenever we will get the point something, at that time we can stop over there, and summation of this all value from the initial moment. So here it is 0. Now summation from this, we will get the 122.92. Again from here it is same. So what we will do here, initial moment is different, and by doing this process we will get the similar moment at the point B. So our aim is that we have to getting similar value at particular joint, and that we will get. Over here also we will get the 93.29. So dear student, we will get this final moment. Now after getting the final moment, we can finding out the SF and BM. It is the same as the slope deflection method. Here also I have taken some another example for understanding this one. So what is over here? Here we have a 3-span continuous beam with different condition. First it is point load at center, and second is UDL over here, and the point load at eccentric. In this case, this example is for simply understanding the procedure, because this is already studied by you in SA1. So what we will get here, first we have to find out the fixed moment A to B, B to A, here B to C, C to B, here C to D, and D to C. So all the equation you know. The most important thing is distribution factor. Here the both end is fixed, then we will get the distribution factor is 0. And for B and C joint we have to take all 4 EI upon L, and summation of these two, we will get the sigma k, and k upon sigma k we will get the distribution factor, that we know. And after that the same process, carryover factor, distribution, carryover, distribution, carryover, distribution, we will get the final end moment. So this is the very much simple method, and from that we will get the SF and BM. Clear? Here some another example is also do practice over there. The same repeated process is done by us with the help of finding out the fixed end moment, the distribution factor, and again carryover. All that things will done by us, and after we will get the bending moment diagram. So this is the most important background for you for the understanding of the frame. Now in the next lecture we will discuss about the how to find out the frame using moment distribution method. This is our syllabus. Clear? Okay, thank you student. We will later on.